Okay, so the idea today is we are going to try to figure out how to set up a power series for functions that do not look like a over 1 minus r. So the past couple of classes, we have looked at how to do a power series for functions that look like a over 1 minus r. And then in the last class, we were looking at when the derivative or integral looks like a over 1 minus r. So I want to talk about ones that don't. And actually, the first one we'll end up doing, excuse me, first one we'll end up doing is either sine or cosine. And so if you do sine or cosine, those obviously don't look like a over 1 minus r. And then the derivative and integral of sine and cosine are sine and cosine, maybe with a negative mixed in, but they definitely don't look like a over 1 minus r. And so what we're going to do, we're going to start by looking at the general case where we're going to say, okay, you have some function that is equal to a power series, the sum k equals 0 to infinity of bk times x minus c to the k. And so we're going to assume for some function like sine or cosine or maybe natural log x or something else, that you have this power series that's equal to the function. And if that's the case, then it takes this form. We get b0 for k equals 0. It's b0 times x minus c to the 0, but x minus c to the 0 is 1. So we just get b0. And then if you plug in k equals 1, we get b1 times x minus c to the first. And then if you plug in k equals 2, you get b2 times x minus c squared, b3 times x minus c to the third, b4 times x minus c to the fourth, and so on. And so then what I actually want to do is I want to look at the derivatives of these. And so if you take several derivatives, you actually start to see a pattern in what's going on here. So we're going to take the first derivative. And we know how to do that from the summation notation based on what we did last week, but I actually want to look at it over here first. So the derivative of b0, that's a constant. So the derivative of that would be the number 0. And then the derivative of this b1 times x minus c would equal b1. The derivative of the next part, you bring the 2 down, so you get 2b2 times x minus c to the first, and then times 1 for the chain rule. And then you get 3b3 x minus c squared, and then 4b4 times x minus c to the third, and so on. And again, you could write that with summation notation, but I actually just want to look at this expansion instead. So this would be k bk x minus c to the k minus 1. I'm not worried about that on what we're doing here. We're going to just look at this right-hand side. And so then I'm going to look at the second derivative. And so the second derivative is 0 for b1. For the next one, the derivative of that is 2b2. The derivative of the next one, I'm going to write it as 3 times 2, b3, x minus c to the first, although obviously that's 6. And then the next one is 4 times 3, obviously 12, but we're going to write it as 4 times 3, not 4 times b. 4 times 3 times b4 times x minus c squared. And then if we think back kind of to what the next one would be, it would be 5 times 4 times b5 x minus c to the third. And I don't have those written where those came from, but that's pretty clear from the pattern. The next one here would be b5 x minus c to the fifth. So we'd have 5 b5 x minus c to the fourth, and then 5 times 4 b5 x minus c to the third in the next line. And so we're going to do a couple more of these. So f triple prime, so third derivative. And I'm going to use this notation. So we can use f triple prime, or you can put like a parentheses 3 here. So when you do that, that's understood to mean the third derivative at of f. So the third derivative of f is equal to, again, 0 for 2b2, because that's a constant. And then the derivative of this part is 3 times 2 times b3 times x minus, or I'm sorry, just 3 times 2 times b3 times 1 for the chain rule. And then plus, now you bring the 2 down, so you get 4 times, so I'm looking at this one, you bring the 2 down, so 4 times 3 times 2, b4 times x minus c to the first, and then 5 times 4 times 3, b5, x minus c squared, and so on. Why do we think that maybe I'm not multiplying these out? So obviously you can, but any ideas as to why maybe I'm not doing 4 times 3 times 2? What are we trying to see here?
Does this have to do with like the a term or something like that?
Has to do with kinda. But what is 4 times 3 times 2 and 3 times 2? And then when you bring this one down, the next derivative, this is going to be 5, 4, 3, 2. What is that when that happens?
It's factorial.
They're factorials. And so that's the pattern that we're trying to get here. So I'm going to go ahead and do one more. So the fourth derivative, and maybe 2 more. Fourth derivative, if we go quickly, is 4 times 3 times 2 times b4 plus 5 times 4 times 3 times 2 b5 times x minus c to the first. And then if we think about it, it's going to be 6 times 5 times 4 times 3 times b6 x minus c squared if we had gone that far above. And then we'll do one more. So the fifth derivative at x, if I go over here, the derivative of this one's 0. The derivative of this one is 5 times 4 times 3 times 2 times b5. Derivative of this next one is 6 times 5 times 4 times 3 times 2 times b6 times x minus c to the first. And that keeps going. Okay, so the idea is this first thing is a factorial, because 5 factorials, 5 times 4 times 3 times 2 times 1. And I mean, there's technically a times 1 there. And then 4 factorials, 4 times 3 times 2 times 1. 3 factorial, 3 times 2 times 1. 2 factorial, 2 times 1. 1 factorial is 1. 0 factorial is 1, which is not obvious, but one of the reasons you define 0 factorial to be 1 is so that this pattern holds up. There's a wide variety of reasons why we define 0 factorial to be 1, but it is. And one of the reasons is this. And so these are all factorials. So this is a pretty clear thing that this first thing is a factorial. When we look at this series, this is just any power series. We said last week that we never know like the interval and radius of convergence of a power series at first, but we do know that it has to converge at the center. And so the center of this series is C, because that's what makes this 0. So what we're going to do is we're actually going to plug in C for all these. So if I plug in C and get f of c here, then if we look at the expansion, f of c, if I put c in for x, nothing happens to this first term. So I get b0 for that. But then if I put c into this one, c minus c is 0, c minus c is 0, c minus c is 0, c minus c is 0. So all of those get zeroed out. And so f of c is equal to b0 based on this. Does everybody see that? Everybody clear? And then f prime of c is equal to b1. F double prime of c is equal to 2 factorial b2. F triple prime of c is equal to 3 factorial b3, because the rest of these get zeroed out. The fourth derivative at c is 4 factorial b4. Fifth derivative at c is 5 factorial b5. And so we can go back and yes, this is b1 and this is b0, but we can write that it's 1 factorial b1 because 1 factorial is 1 and 0 factorial is or I'm sorry, f of c is 0 factorial b 0 because we define 0 factorial to mean 1. And so this is a pretty good argument that fk of c in general is equal to k factorial bk. Now, any questions, first of all, on how we're getting that result by doing this? Does everybody follow what we're doing here? Okay, so let's talk about why this is significant and what exactly it gets us. So you have some function f of x, like sine x or cosine x or e to the x, something that you can differentiate an infinite number of times. And it turns out this would be true even if you can't, even if like these become 0. But anyway, it's an infinitely differentiable function, meaning you continue to take the derivative. We assume there's some power series equal to the function. Okay, so if there's a power series that's equal to the function sine x, for instance, then this is just the general form of a power series. Well, if you look at what's going on with this power series, the only thing that's complicated about the power series is bk, because this is x minus whatever the center is to the k. We know exactly what that does for any value of k. So if k is 30, we know this is x minus c to the 30th. There's nothing complicated about that. B30, that's the significant part, is what is that coefficient? Well, this is a formula that gives us a way to figure out what the coefficient is for any value of k. So we can solve this for bk, and bk has to equal fk of c, the kth derivative at c, over k factorial. And that's the big result here. Does that make sense to everybody, what we're getting? So that tells us what the coefficients of the power series are, assuming there's a power series that's equal to this function f of x. Okay, so big result is that f of x is equal to the sum k equals 0 to infinity of fk of c over k factorial times x minus c to the k. That is the representation that we're going to use for a random function f of x, and we're going to use that to figure out power series for a lot of things. We typically call this a Taylor series. And just a note on notation. So this is a Taylor series centered at C. It is a Maclaurin series. And different textbooks spell this name a little bit differently. I think ours uses an A in it. But anyway, it's a Maclaurin series when the center is 0. Okay, and so a Maclaurin series is a type of Taylor series. I don't know a lot about math history, but it has something to do with two different mathematicians studying this at the same time. But anyway, so this, you could call it a Taylor series centered at 0, or a Maclaurin series if the center is 0. All of these are power series. A lot of the series we found last week would also be called Taylor series or Maclaurin series. Even though we didn't use this, they would have satisfied this. So if we used a over 1 minus r, a lot of those we were doing center 0, and so those were Maclaurin series. That wouldn't change the directions. But anyway, just some terminology. We could call this a Taylor series or Maclaurin series. If the center is 0, we could call it a Maclaurin series. But anyway, we're going to do an example where we do this. And so we're going to derive the Taylor series centered at 0. And we're going to do for cosine. Okay, and so we could, the directions here could say find the Maclaurin series or derive the Maclaurin series for cosine x. It could say Taylor series centered at 0. It could just say power series where we choose the center of 0. All of those would be basically the same. Those are actually the same thing in this case. And so when we do these, what we want to do in general is we want to look at the function that we're trying to find this power series for. And so this is cosine x. Man, that's not very legible. We're going to do that in blue, but it is cosine x. And so if you look at that, the first thing we want to think is, does the series look like a, or does the function look like a over 1 minus r? And cosine does not. And if it does, we do it like we were doing last week. And then does the derivative or integral of that look like a over 1 minus r? And it doesn't either, because they're going to be sine or negative sign, depending on whether you take the derivative or the integral. And either way, no matter what, you never get something that looks like a over 1 minus r. So if that's the case, then we're going to try, if it doesn't look like that, we're going to try this. And so we're going to assume there's a function, or there's a series for cosine x. So we're going to come down here and say, okay, this is equal to the sum k equals 0 to infinity of fk of the center, but the center here is 0, over k factorial, and then x minus 0 to the k, so just x to the k. And that's, so this part is just knowing the center is 0. So we're using the result we got earlier to come up with this. Everybody clear where we're getting that? Any questions? Okay, and then just kind of as a heads up, what we're doing up here, what we've been doing up till now in class, this is like the theory behind getting this formula. And so like, I would like us to understand this theory, but now we're doing an example where we actually use that in order to do the problem. So this is more like what we would normally be doing as part of a problem. So we're going to say, okay, cosine x is equal to this. Now, I'm going to go ahead and write out what the expansion of that looks like. So if I plug in k equals 0, that is f0 of 0 over 0 factorial times x minus c to the 0. And we won't write this out every time probably, but that's what we get when k is 0. And then when k is equal to 1, we get f1 of 0 over 1 factorial times x minus c to the first. And then when k is 2, we get f2 of 0 over 2 factorial times x minus c squared. And for k equals 3, we get f3 of 0 over 3 factorial x, I'm sorry, and man, I should drop the x minus c. We're just going to go with x to the 0, x to the first, x to the second, because we already knew the center is 0. My fault, guys. So we're going to put x to the 0 here, x to the first here, x squared here, and x to the third here. Because c was 0. So it wasn't wrong to put the other thing, but we already knew c was 0, so we can just go with this. All right. So this is what the expansion looks like. Now, the thing that is important about that is the only hard part is the top. So this, like f2 of 0, means the second derivative of f evaluated at 0. This is the third derivative of f evaluated at 0. This is the first derivative of f evaluated at 0. This is the 0th derivative of f, which means the original function evaluated at 0. And so for any random k, if k is like 39, the only thing that's hard is the 39th derivative. We know the bottom when k is 39 is 39 factorial, which is just a constant. And then x to the 39th is a simple expression. The top is not. The 39th derivative evaluated at 0, that's something that's complicated. So what we do is we try to find a pattern in what's going on in the numerator. So you make a list of the function and a bunch of its derivatives. So the function itself is cosine x. And now we take the derivative of that. So the first derivative is negative sine. The second derivative is negative cosine. The third derivative is positive sine. Fourth derivative is cosine. Fifth derivative is negative sine. Sixth derivative is negative cosine. And if you notice, this is just cycling. It's cosine, negative sine, negative cosine, sine. Cosine, negative sine, negative cosine. Next will be sine. And it just cycles through those four forever. You want to make this list until there's a clear pattern, if there is one. So you want to keep this list going until the pattern is fairly clear. So you make a list of the function and a bunch of its derivatives. Then you plug in the center, because what we're worried about is like not just f2 of x, we want f2 of 0. So we now make a second list to the right where we plug in 0 for x. So f of 0 is cosine of 0, which is 1. F prime of 0 is negative sine of 0, which is 0. F double prime of 0 is negative cosine of 0, which is negative 1. The third derivative at 0 is sine of 0, which is 0. Fourth derivative at 0 is 1. Fifth derivative at 0 is 0. Sixth derivative at 0 is negative 1. Okay, so you make a list of this function and its derivatives, then you plug in the center and you want a clear pattern. So this is 1, 0, negative 1, 0, 1, 0, negative 1, and then it'll be 0, 1, 0, negative 1, 0, 1, 0, negative 1, and forever, like that. Okay, so now we're going to continue with this expansion down here. And so like I said, a lot of times we don't write this first step, but if we now go through and plug in, okay, so f0 of 0, that's the 0th derivative evaluated at 0. So this entire numerator gets replaced with this answer 1. And so we get 1 over 0 factorial x to the 0. So that's coming from this list up here. f1 of 0, that's the first derivative of 0, based on the second one is 0. When that happens, so this whole top is 0, that zeroes out the entire term. So the k equals 1 term is 0 divided by 1 factorial, but that's 0. And then 0 times x is 0. So this is 0. f2 of 0, that's off the list. That's negative 1. So we get negative 1 over 2 factorial x squared. f3 of 0 is 0 over 3 factorial x to the third, but that's 0. The next one, which I didn't write up here, would be f4 of 0. Well, that's positive 1 over 4 factorial x to the fourth. f5 of 0 is 0. f6 of 0 is going to be negative 1 over 6 factorial x to the sixth. And so on. Questions to hear, because I know this is really weird. Does anybody have any questions so far? Okay, now what we want to do is we want to take this sum and you want to simplify, but you only want to simplify stuff that simplifies consistently throughout the series. So like, if you look at this first term, 0 factorial is 1 and x to the 0 is 1. So this whole thing is 1, but nothing that easy happens to any of the other terms. Like this doesn't simplify at all. This doesn't simplify at all. And so you don't want to simplify that down because nothing like that happens later. But the 0 terms can all drop out of the equation. So when we look at this, we can say then, okay, this is equal to 1 over 0 factorial x to the 0 plus negative 1 over 2 factorial x squared plus 1 over 4 factorial x to the fourth plus negative 1 over 6 factorial x to the sixth. Does everybody follow what I'm doing? So we're just dropping the 0 terms from that expansion. Okay, now what I want you to do is take a minute, just a few seconds. I'm going to kind of mute it for a minute and just let you guys do it, but come up with the next 3 non-zero terms. So write what the next 3 non-zero terms are, and then we'll do it together in just a second. Okay, so the next three non-zero terms would be 1 over 8 factorial x to the 8th plus -1 over 10 factorial x to the 10th plus +1 over 12 factorial x to the 12th. Okay, so now the idea is, remember, we're trying to come up with a series for cosine x. So this is the series for cosine x. We're going to now put this back into sigma notation. The issue is that we dropped half the terms, so the numbering changes. So the numbering at this point, we can start wherever we want. We're going to, like I said, we're going to write a sigma notation. So we can start at k equals 0 if we want. We can start at k equals 1 if we want. I'm going to choose to start at k equals 0. But if you start at k equals 0, then the next term has to be k equals 1, not k equals 2. The next one is k equals 2, k equals 3, k equals 4, k equals 5, and k equals 6, and so on. And so what we're trying to do is come up with a formula for this. Well, there are three things that are happening. You've got a numerator, a denominator, and then a power of x. So the numerator is alternating 1 to -1. -1 to the k works for that. And the idea is if I plug in 0 for k, I get -1 to the 0, which is 1. If I plug in 1 for k, I get -1 to the first, which is -1. If I plug in 2 for k, I get -1 squared, which is +1. 3, -1 to the third gets me -1. So remember, we're coming up with a formula where if I plug these in, I should get these terms. Does that make sense to everybody? That's good. Okay, the bottom, there's a factorial, and they're all even numbers. In this case, the even numbers are 2k factorial. And again, we can check that because if I plug in 0, it's 2 times 0, which is 0 factorial. 2 times 1 is 2 factorial, and then 2 times 2, 4 factorial, 2 times 3, 6 factorial, and so on. And then x to the 2k, and here the factorial matches that power. So we get -1 to the k over 2k factorial, and then x to the 2k. That is the Maclaurin series for cosine. That's the Taylor series centered at 0 for cosine, the power series for cosine, and so on. All right, any questions to there? So cosine x is actually equal to that series. That's good. Okay. I didn't ask because of time. I didn't ask for the interval and radius of convergence for this power series. So I just asked to derive the Taylor series centered at 0. We've done that. If you're asked for the interval, radius, and convergence, you would use the ratio test on this series. So like we were doing last week, we did that sometimes with the absolute value of r is less than 1. You do that if you're using a over 1 minus r, but if you're not, like we're not here, then you do use the ratio test. When you do the ratio test, you get 0. That means that the interval of convergence is actually -infinity to infinity, and the radius of convergence is infinity. We would show this, use ratio tests to get this. Okay, any questions so far? Okay, so what I'd like you guys to do is actually take a minute to get started, and we'll work it together, but I want you to find, or derive, we'll say, meaning you have to show all this stuff. So derive a power series, Taylor series, whatever we want, for f of x equals sine of, we'll do 3x centered at x equals pi over 6. You know what? I think we're just going to work it together. If you think you can do this on your own, that's fine. Work it. But I want to just go ahead and start this together because it's kind of a lot. based on what we're doing. So, okay, so again, this is one where it's not one that looks like A over 1 minus R. The derivative doesn't look like A over 1 minus R. And so we're going to use Taylor's formula in order to do this. Excuse me. So we're going to write out, okay, sine 3x is equal to the sum k equals 0 to infinity, fk at the center. The center is pi over 6 over k factorial times x minus pi over 6 to the k. I may change my mind on what I want to do. Yeah, I'm sorry. I want to center this somewhere else. We're going to center this at pi over 3. I want it to work a little differently than the other one did, and it's going to be real simple otherwise. All right, so we're going to make it pi over 3. That means down here, this is going to be pi over 3, and this is going to be pi over 3. Other than that, no change. All right, so we're going to center it at pi over 3. All right, so now when we do this, we could write out this first step, but it's just going to be like f 0 of pi over 3, x minus pi over 3 to the 0 here. So that part, we don't really need that step. The complicated part is the numerator of this. So what we want to do is make a list of the function and a bunch of its derivatives until there's a clear pattern. So f of x is obviously sine of 3x. F prime of x is 3 cosine of 3x because of the chain rule. So the derivative of sine is cosine. Chain rule gets you times 3. The second derivative is then negative 9, but we're going to write it as 3 squared so that we can see a pattern. So negative and then 3 squared sine of 3x. The third derivative is negative 3 to the third. It would be 27, but negative 3 to the third cosine of 3x. Fourth derivative is positive 3 to the fourth sine of 3x. Fifth derivative is 3 to the fifth cosine of 3x, and then that's going to keep going. So, okay, it is cycling through sine, cosine, negative cosine, but we're getting powers of 3. So we've got 3 to the first, 3 squared, 3 to the third, 3 to the fourth, 3 to the fifth. Back up here is 3 to the 0, which is good. So that also fits the pattern. And so now what we want to do, though, is we want to plug in pi over 3 for all of them. So we're going to go through and now do f of pi over 3. Well, that's sine of 3 pi over 3. That's sine of pi, which is 0. So sine of pi is 0. F prime of pi over 3 is 3 cosine of 3 times pi over 3. That's 3 cosine of pi. Cosine of pi is negative 1, so that's negative 3. So everybody follow what we're doing? Any questions? Okay, now we're going to plug it into the second derivative. So the second derivative at pi over 3, that's negative 3 squared times sine of pi. You can kind of see that every time you plug it in, you get 3 times sine of pi, or 3 times pi over 3, which is pi. Sine of pi is 0. Third derivative is negative 3 to the third cosine of pi. Cosine of pi is negative 1. So it's positive 3 to the third. And then we can if we start to see the pattern, this one's 0, and then this one is 3 to the fifth times negative 1, which is then negative 3 to the fifth. And then that keeps going. Any questions so far? Okay, so we're going to write out the expansion. So now we're going to plug in k equals 0. And so if I plug in k equals 0 to this, that's f0 of pi over 3. That's what I get off the list. Well, that's 0. So that zeroes out the entire term. All right, so it'd be like 0 over 0 factorial x minus pi over 3 to the 0. That zeroes out the whole thing. Now we go to k equals 1. So k equals 1 gets me f prime of pi over 3. So f1 of pi over 3, that's off the list. So the entire numerator gets replaced with -3. So remember, this notation is not like fk times pi over 3, it's fk of pi over 3. That's what we're getting from this list. So that whole numerator is -3. The bottom is 1 factorial times x minus pi over 3 to the first. K equals 2 we get from the list. So k equals 2 gets me f2 of pi over 3. That's 0, so that zeroes out the whole term. K equals 3, f3 of pi over 3, that's 3 to the third over 3 factorial x minus pi over 3 to the third. K equals 4 gets us 0, and k equals 5 gets us -3 to the fifth over 5 factorial. And I'm going to shove this down here, x minus pi over 3 to the fifth. My bad, guys. So it's right there. Those two are multiplied together. Run out of room on the screen. All right. So now we're going to drop the 0 terms and simplify down some. So we get -3 over 1 factorial x minus pi over 3 to the first plus 3 to the third over 3 factorial x minus pi over 3 to the third plus -3 to the fifth over 5 factorial x minus pi over 3 to the fifth. And now what I'd like you to do is take a second and come up with the next 2 or 3 non-zero terms. So at least the next 2 non-zero terms. Okay, so the next non-zero term would be 3 to the 7th over 7 factorial, x minus pi over 3 to the 7th, and then -3 to the 9th over 9 factorial, x minus pi over 3 to the 9th. Everybody good? Okay, now we're going to write out a summation notation for this. So again, we can start wherever we want. I'm going to choose to start at k equals 0. But when I start at k equals 0, I don't get to jump. This is then k equals 1. This is now k equals 2. This is now k equals 3, and so on. So the numbering is no longer the same as it was on that first line because we dropped all of the 0 terms. So now there's a couple things going on this. So we've got the top alternating. So it's negative, positive, negative, positive. For that to happen, we're going to go with -1 to the k plus 1 here. Okay, so -1 to the 0 plus 1, that's -1 to the first, which is -1. If I plug in 1, 1 plus 1 is obviously 2, -1 squared is 1. If I plug in 2, -1 to the third is -1, and so on. So that gets me the alternating part. Then we have a power of 3, but those are odd powers of 3. odd numbers are an even number plus or minus an odd number. So 2k is a bunch of even numbers. If I then add 1, that works here. It might be -1 in some cases. It might be +7 in some cases. But if I plug in 0, 2 times 0 plus 1 is 1. 2 times 1 plus 1 is 3. 2 times 2 plus 1 is 5, and so on. And then the bottom, that's 2k plus 1 factorial. And then x minus pi over 3 to the 2k plus 1. And so this is the Taylor series or the power series centered at pi over 3 for sine of 3x. So we got the sine of 3x is equal to that. And again, because of time, I didn't want to do the interval and radius of convergence, but these would be negative infinity to infinity for the interval. And the radius of convergence then is infinity. And you would get that using the ratio test, but we've not shown that part. All right, questions on this problem?
For the -1 to the k plus 1, why isn't it just -1 to k?
Because we need it to alternate this way, where this one's negative, this one's positive. So the idea is if I plug in 0, I get 0 plus 1, which is then 1. And -1 to the first is -1, which is what I want. And then if I plug in 1, 1 plus 1 is 2. -1 squared is +1, and I want this one to be positive. Does that make sense?
Yeah, because I was just looking at because the last one there was just -1 to the k.
It was, and there, because now k equals 0, I want that one to be positive. So -1 to the 0 is +1. -1 to the first is -1. K equals 2, I want to be positive, and so on. So it has to work for these values of k to get the negative or the positive that you need. Does that make sense, Jordan? I know that's confusing. Does it?
Yeah, that makes sense. Thank you.
Okay, yeah. Other questions, you guys? Okay, so then we're going to do some more examples of those tomorrow. I want you to I want to show you this worksheet. I really don't want you doing a bunch of homework over this week. Definitely after tomorrow. I don't want you to do any homework until next week because of the holiday. But if you do want to practice before tomorrow's lecture, just a couple. This is in the shared drive. Give me 1 second, and I want to tell you the problems to look at. So in Unit 3, Folder 2, nope, Unit 4, sorry. Unit 4 is Power Series, Folder 2, and then the Power Series 3 worksheet. So let's write that down. So Unit 3, or Unit 4, Folder 2. And then there's the Power Series 3. Okay, so this is the worksheet that goes along with today and tomorrow's lecture. Whoops. Is it showing that? Can you guys see the worksheet? Yeah, okay. So Derive a Maclaurin series for sine, that one would be a good one to practice, centered at pi for cosine, similar to the one we did. And then these, we're going to do e to the x and log x tomorrow. And we're going to talk about the rest of these. If you have time, it would be good. It would help you before tomorrow's lecture to have just gone through this process on your own a couple times. I would do the first 2. But again, this is Thanksgiving week. If you want to take the night off, that's completely fine if you just want to watch this lecture later. But whenever you're watching these videos, after today's video, before tomorrow's video, I would recommend that you do the first 2 problems on the Power Series 3 worksheet. You have solutions to those so you can check it just to kind of get this process down. And then we're going to talk about how this applies to e to the x and natural log x tomorrow. We're also going to talk about, given a simpler series, how do you find one that's more complicated? So those will be the 2 main topics tomorrow, and that'll actually wrap up what we're going to do with Power Series this semester. So if you have any last minute questions, stick around. If not, I will see you guys tomorrow. Or if you want to take the break off and watch these after break, that's completely fine too. Have a good Thanksgiving if I don't see you. And if you have questions, stick around.